He wants to know if we're out and if the coast is clear.
Well, we're not, and it isn't, and it's not going to be.
If you love listening to this show, please consider giving a rating and a review on Amazon Alexa or wherever you listen. We want to continue bringing you this amazing content, and part of our ability to do that means that we need a big audience. Now, it may not seem like much, but rating and reviewing the show will help more people find us, just like how you found this show. Simply on any podcast platform, search for our show, scroll down to the bottom, and push 5 stars. It's that easy. Thanks for supporting the show. Today, I'm joined by Benny Bowler, who is the founder and CEO of VELO3D. Now, VELO3D provides comprehensive additive manufacturing capabilities. Benny, thank you for joining us today.
Thank you. It's my pleasure, and I'm very excited to be here.
All right. So you've actually spent many years in your career at companies like Applied Materials, First Solar, and you understood very early on, especially, of course, your educational background as well, the importance of high precision and how even a small defect or flaw could affect semiconductor performance or solar cell efficiency. Can you tell us a little bit more about your background?
Yeah. So I'm a physicist in background, an electrical engineer. I spent the first 10 years of my career in the technology unit of the Israeli intelligence. I got the National Security Award from the President of Israel when I was 28. Later on, I joined, and in this unit, without divulging too much, we basically worked on Mission Impossible projects. And always these were projects with very urgent delivery to operational customers. I joined Applied Materials and worked on semiconductor equipment, really inspection with nanometer resolutions, and later on mask writing for the masks that are used to produce the chips, to pattern all the layers in semiconductor production. I was also the vice president of technology for PV modules in First Solar, which has been the largest and to this date is the most profitable solar company in the world, solar module company in the world.
Well, I think you're clearly being very modest about your background, but you've had a tremendous amount of success, and now you guys are working on something fairly sizable. We'll get into some of the key milestones that you've hit even more recently as well. But I want to talk a little bit about the context of the pandemic. So early on with COVID-19, we saw some pretty serious manufacturing, supply chain, and logistics problems that were caused for certain industries because they couldn't, depend on their, suppliers or subcontractors. So my question is, how does distributed manufacturing capabilities for critical components help to address the local product availability and timeliness, which has become even more important than ever before?
Yeah, I will give you a metal additive manufacturing context for this answer, because this answer could be very rich. And in the context of metal additive manufacturing, when you think about production of high complexity, high performance metal parts, there are a lot of parts with lead times that are measured in quarters, 3 quarters, 4 quarters. And when the lead time for specific parts is measured in quarters, then the lead time of delivery of systems is measured in years. And this applies both to manufacturing as well as to service or provisioning of spare parts to operational systems. Additive manufacturing has the ability to reduce the lead time from quarters to weeks or even days. We are not talking here about supply of parts on demand, where you can get the parts within hours. We are talking here about shrinking the lead time from quarters to days or weeks. The implication of that is dramatically reduced inventory, as well as dramatically reduced supply chain risks and disruptions to both service and production. Where we see this often in oil and gas, in power generation, and in aviation is in systems. You see this most painful in systems where the number of parts that are used is relatively small, in the tens or in the hundreds a year, and it's distributed across many users, resulting in many users having to store inventory in case they will need the part, even though they consume less than one part a year on average, resulting in very large inventories. And often people are balancing these inventories and finding out that the parts that they actually need this year, they didn't store, and they have disruptions. So this is a very big opportunity for additive manufacturing to make companies much more agile and lean in their operation.
That's a really great way to describe the kind of business problem in terms of the fact that, if they're sitting on inventory that's essentially cash, that's just sitting on the shelf, that's not being actually utilized. And then to your point, even if you think that you have the parts in stock, it turns out that maybe you don't have the right parts, so you're still out of stock. Correct. Let's get into your company. What is VELO3D, and tell us what you guys are doing on the additive manufacturing side.
Yeah, so to answer this question, I will start with a little bit more philosophical answer, which is, why do people move to additive manufacturing in metals to begin with? Why companies in the energy and in the aerospace industries move to additive manufacturing to begin with? We touched upon one example, which is supply chain agility and de-risking of supply chain. The other reason is because additive manufacturing, in principle, allows you new manufacturing capabilities that allows you to design systems with higher performance, because you can now make design choices that you couldn't make before because of the increased capability of the manufacturing. This idea is sometimes captured in the term design freedom or geometrical freedom. What people actually don't know is that there are actually very severe design constraints on manufacturing with additive manufacturing. So additive manufacturing has a lot of limitations that are very unique to it, and that are very different than any of the limitations that you find in any other manufacturing technology. This means that when people try to design these high-performance systems, moving to additive manufacturing in order to get better products, they actually find a really big stumbling block, which is they design the optimal designs using very sophisticated simulation capabilities, etc. And then once they have them, now they have to bastardize them and compromise them to get to something that is manufacturable, very often erasing the vast majority of the benefit. In a similar way, these legacy parts that I described to you in the first part of our conversation were not designed for additive manufacturing. So in order to apply additive manufacturing for them, you very often need to redesign them in order to make them additively manufactured. These are the two applications where we actually solve this problem in the most fundamental way. The vision of VELO is to provide additive manufacturing technology that is truly universal and is truly all capable. In other words, we truly strive to a point where you as a designer could design the optimal product, and our role is to be able to produce that without having to tell you, you can't do that and you can't do that. And really allow people to get to the ultimate in why they came to additive manufacturing to begin with, which is to produce the optimal parts that they need, and to be able to take parts that were not designed for additive and that they want to shrink the supply chain, and be able to do that seamlessly and easily. This is the core of what VELO3D does. As soon as you start to do that, you find that there is another challenge, which is the challenge to provide quality certification and quality assurance on the parts that you are producing, because all these parts are very mission critical parts. So the next layer that we added is the ability to provide quality assurances. And that relates to my history in semiconductor and in photovoltaic and solar.
Yeah, I think this notion of design freedom, which again is difficult even outside of the context of additive manufacturing, but the fact that designers or engineers can actually design for true optimization, which is really rare because to your point, once it gets into a manufacturing process, it kind of gets muddled down and there's a lot of compromises, like you said.
Exactly.
So the fact that they can actually truly target for optimization and be able to execute, even in the context of additive manufacturing, gives them a tremendous amount of freedom and versatility, like you're saying. And then the part that I was going to ask you about is exactly the certification, which is that so they have the freedom, but now they also have the assurance and the confidence that it meets the industry standard in terms of quality. Because
Correct.
to your point, these are very, very critical components where if it fails, the whole system could potentially be in jeopardy.
Correct.
Speaking of, so you guys have been doing this for many years and really have reached some incredible milestones. Summer of this year, your company announced, I believe, one of the largest orders to date, a $20 million purchase order from a major aerospace customer. Can you tell us about that and what led you to this key milestone?
Yeah. So unfortunately, I cannot divulge identifying information about this customer, but um, this customer has been producing engines using our technology. And specifically, this is a new generation engine, and they have accomplished tremendous performance improvements with this engine, partly enabled by our manufacturing technology. So when this company started to adopt our technology, they realized that they had very few parts where they were making very serious performance compromises using existing additive manufacturing technology. And they wanted to test our technology in order to be able to overcome these limitations and get higher performance. As they started to implement that, they found that there are more and more opportunities in the engines where they're making compromises and they could get higher performance if they utilize our technology. And they migrated another part and another part and another part. As the company has been scaling production, they needed more and more printers. And this last order is an order that is required for them to get their next milestone in scale up, allowing even more parts to be serially produced on our system.
Yeah, I love this story because you're essentially an embedded capability that supports the next generation or the evolution of new components and systems that really pushes the boundary in terms of performance. So that's very, very exciting. I want to get into some specifics around your printer. So if you could talk about your metal LB PBF 3D printers and why it's so superior relative to competitors. And then also yours, I don't know if it's within the same category or not, Sapphire printers that's capable of fabricating production grade titanium, aluminum parts, and other precious metals.
Yeah, so LPBF stands for laser powder bed fusion. This is the standard term for this technology. There are other commercial terms for that that some of our competitors have put, like DMLS and DMLM and SLM, but these are all terms that represent the same fundamental manufacturing technology. This is a commodity manufacturing technology that has been invented almost 30 years ago, more than 25 years ago. And so that's what LPBF stands for. Sapphire is our printer in this LPBF family of solutions. And LPBF or laser powder bed fusion represents, in my estimate, about 80% of the metal additive manufacturing market. So this is the dominant technology in metal additive manufacturing market, 3D printing. The Sapphire printer is part of our solution, which also involves the software that drives the Sapphire called Flow, and the quality assurance software that's called Assure. So this is part of one solution. All those are powered by our proprietary manufacturing process that is prescribed by Flow, executed by Sapphire, and validated by Assure. The core unique capability that is provided by Velo is the technology capability that we termed support free. So the fundamental limitation that you see in all metal laser powder bed fusion systems is that when you get to angles as you are building, so imagine you're building a part very much like you're building a building in construction. When you have features that are less than 45 degrees in their inclination angle, you need to support them. Very much like you have to support an arch or a ceiling of a building while you are constructing it. This supports or scaffolds. If you think about how you're constructing a building, when you're finishing the production or the construction of the building, people come in and take the scaffold and then sometimes get the scaffold, and put them on the next floor as you're building the next floor. Unfortunately, for mechanical parts, you don't have the little people that will come in through the internals of the part and will remove these supports. So these supports create a very fundamental limitation on what you can produce with additive manufacturing. Because every time you have these supports in places that are hard to access, it means that this is a part that is very hard to produce by additive manufacturing or not practical to produce by additive manufacturing. The paradoxical thing in this type of complex parts with complex internal features are exactly the parts that are difficult to machine and that would be great candidates for additive manufacturing. These are the complex parts that you would actually want to produce by additive manufacturing. So the paradox is that the parts that are going to be the most valuable and most immediate candidates for additive manufacturing are also the parts that are not really producible unless you compromise their designs to avoid these limitations. So this capability to provide support-free manufacturing, basically we eliminated the need to add these supports as you build. In laser powder bed fusion, in all laser powder bed fusion, you have natural support that is provided by the powder. So in laser powder bed fusion, you lay out a layer of powder, then you use laser to solidify the metal where you want the object to be, then you lay out another layer of powder and you kind of build the object in layers like burying a dinosaur skull in the sand. At the end, you have the part that you can extract from the sand, from the powder, and the powder is completely flowable and you can remove it. But the reason why existing laser powder bed fusions require support is not to actually support the part. These supports are more anchors that are holding the part together from curling on itself up and destroying itself in the production process. As you are laying the next layers, it would collide with the mechanism that laying the next layers. So the solution that we have is preventing the part from curling and destroying itself in the production process, eliminating the need to anchor it down while you are producing it. If that was not so technical.
No, makes sense. I mean, so basically you're talking about this this capability that houses a non-contact recoder, right, to reduce the risk of part collision and in situ metrology sensors. It's very interesting, and of course, a lot of these techniques. I wonder, how your time, again, going back to your early time at Applied Materials and First Solar, helped you to solve technically to be able to get to this level of maturity on the product.
So probably the most relevant experience I had that enabled me to think about what we are doing right now is the work that I did in Applied Materials on the mask printer in Applied Materials. And when you're trying to print features with really nanometer resolutions, you find that there are a lot of mechanisms that are distorting the prints and are causing errors. And we created a very sophisticated layer, multiple layers of corrections and algorithms to understand what are these distortions that are happening and what are the errors that are created, measuring them and correcting them as they are being created. This is actually the fundamental of what we implemented in our manufacturing technology. So what we realized is the reason why you need to have supports in conventional systems is because as you are trying to make the parts, you are producing the part in a wrong way, because you are producing the part in a way that is kind of like average, that is a compromise, that is appropriate compromise for most of the things that you need to do. But it's actually not the right way for anything that you're trying to do. So the idea that you apply a manufacturing process that is optimal in every point to the locality where you're building it, and the idea that you can create algorithms that will identify what are these different localities and what is the right process for those. This has been the core idea that we, if you want, stole from the semiconductor area and applied to additive manufacturing.
Well, this is very, very intriguing, very exciting. Slightly changing topic, but actually still holding on to what we just discussed, is that most of the focus for you guys has been in aerospace, oil and gas, and power generation. But I wonder, within aerospace specifically, space as it pertains to like the ISS and eventually the lunar moon station and other types of capabilities that's going to be needed in space, including if you think about components for satellites. So satellite maintenance and servicing is going to be a big issue as well. And of course, sending anything into space, there's a huge, cost of transportation involved. How does your kind of capability play a critical role in the building of not only critical mission components, but the ecosystem to build out industrial capabilities in space and on moon?
Yeah, so I think the most critical element in this is the reduction in cost of launching an object to space. So for a very long time, humanity was in stagnation for about 30 years in the cost of launching a kilogram to space. In the last 20 years or 15 years, we have seen dramatic cost reduction in the cost of launching objects to low orbit as well as outside the Earth orbit. Our technology is dramatically helping that because there is a very non-linear effect of efficiency of engines on the cost of launch. Because as you are launching, what you are launching is mostly fuel. Very little payload and mostly fuel. And this fuel is used to propel the rocket. The more efficient is the engine, the less fuel you need to launch in order to get payload out. So the amount of payload that you can get is disproportionately related to the efficiency of the rocket engine. So getting even small efficiency improvements on the rocket engines creates a very non-linear dividends in the cost of launch. Being able to reuse rockets creates a tremendous benefits for the cost of launch, because the vast majority of the cost of launch is the cost of the rocket, not actually the cost of the fuel. So the ability to increase the efficiency of the engines, as well as the ability to make engines that are reusable and that are reliably reusable, are two very critical areas that we are critical component of this improvement.
Yeah, we're really glad that you highlighted those points, especially on the reusability, because efficiency, of course, is something that from a design they're probably constantly striving for. But being able to have the longevity and the versatility to have multi-mission, multi-launch, and still be able to retain the integrity of those components, those systems, is like I say, mission critical. So the design approach has to be fundamentally different from, let's say, a single-use rocket, for instance. Can you go into, again, not sure if you've directly worked on these types of projects, but can you go into maybe the science of how your printers and your approach would actually help those engines to be able to actually survive several missions.
So if you think about this, when you're launching once, the load profile on the engine is very short. You have to survive few minutes of operation. In terms of fatigue, you don't go through a number of cycles of heat and cold. In terms of oxidation, you can have the engine oxidized, and all you care is that it will not oxidize fast enough before the launch is complete. When you go to reusability, each one of those problems are problems that you have to solve. So you can't, you have to make sure that the engine and the parts in it are sufficiently reliable and strong to be able to withhold a number of cycles of massive heat up and massive cool down. You have to be able to make sure that the parts don't creep during a number of consecutive launches to the point of failures. And you have to make sure that the parts are sufficiently oxidation resistant in all these intense oxidation conditions. So these are all examples of problems that need to be solved that are creating bigger design challenges for the engineers designing those engines. And those engineers now need more creative solutions to maintain high temperature in the engine, in the gas, but at the same time efficiently cool the parts to create light parts, but at the same time to make sure that the parts are as strong as possible and have enough engineering margin to withstand the number of cycles that you have to do. So all these are design that are making the design of the engine that much more creative and that much more challenging, requiring new design space and and more capable manufacturing technology allows people to explore this design space.
Well, this is so relevant for today's market and, of course, where things are going within space as well as the other sectors that you're covering. So today I've been joined by Benny Buller, who is the CEO of VELO3D. Thank you for joining today.
Thank you so much. It was really a pleasure. I really enjoyed this conversation.
If you've enjoyed this episode, take a moment to rate our show on any podcast platform that you listen to. Scroll down to the bottom and push 5 stars. It's that easy. And as always, thanks for listening.